I was saying, last Friday we were discussing the nature of dissociation, and then how that applied to the electrolytic properties of solutions. What types of compounds dissociate when put in water? Ionic compounds. And how do we know what an ionic compound is? It has a metal in it with one exception, the ammonium ion, which is the one, a positively charged ion that would also be included there. Okay. We also saw that the amount of electricity that could be transferred, or in other words, the extent of being electrolyte was governed by the concentration of these substances. As we found out, the more stuff that dissolved, the more ions there were, the more electricity could be conducted. We got to see that too, right? Now, the one thing that I did not get to do, because we ran out of time, and I'm not going to do it now, or I'm not going to do it. I'm going to talk about it. We said there were three types of dissociation. We said there was electrolyte, strong electrolyte, weak electrolyte, and non-electrolyte. I did not give you an example of a weak electrolyte as far as with the light bulb. Correct? Okay. But I think we did talk about the fact that what it meant, it was an equilibrium scenario, and I think it was acetic acid that I put up here. In your notes, you may have that down. Okay. So when it talks about partial dissociation, they either completely separate or they don't separate. I just want to make sure we're clear on that. Okay? They don't kind of separate. Okay. I just want to make sure we're clear on that. All right, moving on. There's a little summary that we didn't get a chance to look at because we were doing the demonstrations. But as it says, the strong electrolytes have high conductivity. We have a total or nearly total degree of dissociation. And some examples. This is a very small list of examples. Hydrochloric acid is a strong electrolyte. Most salts, meaning ionic compounds, are. The strong bases. We're actually here in a minute or two. We're going to learn what it means to be a strong base, a weak base, a strong acid, a weak acid. And then so the strong bases include the group 1A and 2A hydroxides. However, for reasons that I briefly touched on the other day, we're going to find out that magnesium hydroxide and calcium hydroxide aren't very soluble in water. And again, it's that force of attraction between the ions because the magnesium ion and the calcium ions are relatively small. So even though they do, to the small extent that they do dissolve in water, they're strong electrolytes, meaning they completely dissociate. It's just you can't get very much dissolved in water. Does that make any sense what I'm saying? They're not very soluble because the ions have a very strong attraction towards each other. The water's not able to overcome that, but to the small extent that they do dissociate, they completely dissociate. Yes?
So weak electrolytes, do they completely or nearly completely dissociate?
No, they partially dissociate.
So what's the difference between strong ones completely or completely or nearly completely dissociate? But then you said for weak electrolytes they either do or don't.
What I'm saying, okay, and again I'll go back to that because that's a big part of what we're doing in chapters later in the year. Okay, I'm going to put acetic acid up here once again as an example. I'm also going to, the one that I had back there to do that we're not going to do is ammonia. And I'm going to go ahead and talk about this now because it's going to come up again. When we put this in water, acetic acid, again, which is the main ingredient, this is what vinegar is, okay? It's an equilibrium scenario, meaning that it does dissociate into hydrogen ions and acetate ions. Okay? However, as soon as this dissociation occurs, the attraction of these two things to each other is strong enough that it immediately starts reforming this. So, give me a second here, I can actually give you some numbers. If we had a 0.1 molar solution of vinegar, acetic acid, okay? What? Geez. So if I were to dissolve this in water, this is the concentration of hydrogen ion that would result. This is the concentration of the acetate ion that would result. This is the concentration of the acetic acid that would result. Joe, that was a very appropriate puzzled look on your face. It's coming. This is it. This is it. I know. This is it. This is where we are. Well, it's similar to it. Joe, what's the problem here?
0.0013 is not equal to 0.1, and even if you add them up or anything.
Nope. But yes, it does. You okay with that?
No, I'm not okay with that.
What's this equal to? And since we're doing addition here, we're limited to the decimal place, which is right here. It's negligible. It's a negligible extent of dissociation. Did it happen? Yes. It's negligible relative to the initial amount. It's like me walking up, and I did this example last year, and coming up to Emily. Emily weighs herself on the scale this morning before she comes to school. She weighed 115 pounds. I'm going to come up. You're welcome. I came up and pulled a hair off of her head. Does she still weigh 115 pounds? No. Is her mass less? Yes, but the scale that she's currently standing on, is it going to say anything different than 115 pounds? No, it's not. Why not? Because the instrument was not capable of detecting that small amount. The instruments that were used to make these measurements were not capable of measuring that small of amount. It was a negligible amount. So, yeah. So where I'm going with this is there's all three of the particles that are in water at the same time. Okay? Whereas if we took sodium chloride, and I tried to get this across to you yesterday or the other day, if I had 0.1 molar of this, when the dissociation was done, okay, the NaCl would be 0, and the sodium would be 0.1 molar. And the chloride would be 0.1 molar. There's the discussion we had this morning, Gracie. Do you see the difference between the two?
I don't understand how the top works.
I'm asking you.
Yeah.
Do you see the difference? So when I say partial...
Go back and forth again.
Yes. It's in equilibrium. Okay? So at equilibrium, all three species are existing simultaneously. This is not an equilibrium scenario. The only things that are going to exist are sodium ions and chloride ions. This is a strong electrolyte. This is a weak electrolyte. Because not all of it has dissociated. Why am I spending so much time on this concept? Because this is really, really important. Go ahead.
Okay, I don't understand why you did not subtract
Okay, you're right. You're right. My bad. Okay, my bad. What's that come out to? There's somebody, seriously, I need the number because it's important. It's
974. 0974.
Okay, so now, to the correct number of significant figures, that was my bad on that. Okay, I meant to add these two things and subtract that one. Yeah, I got in it. Yeah. So did this decrease? Yes, but by a negligible amount.
Right.
Okay. All right. That was huge right there, people. You don't even know how big. This is the entirety of chapters 16 and 17. Doing the math to get to that number right there. All right, moving on. Mark it down. Did you get it? Okay. All right. Okay, weak electrolytes. Low to moderate conductivity, would an acetic acid solution or a ammonia solution, I didn't do ammonia, would those conduct electricity? Yes, to a very, very small extent. We would barely see that light glowing. What are some examples? The weak organic acids, I'm going to introduce this here in about 18 seconds or so. And the non-electrolytes are going to have no conductivity. I think I did sucrose. Did I do sucrose? Yeah, and nothing happened, of course, right? And because there is no dissociation. And what are some examples? Well, any of the sugars, okay? But notice what I also put on there. AgCl, silver chloride, and iron 3 oxide. What do we know about those compounds? They're ionic compounds. So why did I put them as being non-electrolytes? No, they're special because of the thing that we've already discussed. They are insoluble in water, or close to insoluble in water. And that's all of Chapter 17, by the way, determining to what extent even an ionic compound is soluble or not. Yes?
The more likely something is to dissolve, the stuff that has a higher pull on water. Does that mean that dissolve?
Higher pull on water. You got to look at it the other way around.
The higher, the force of...
The Coulombic force of attraction between ions?
Yes.
What about it?
I'm saying that if something has a higher force than another substance, does that mean it dissolves faster than another?
Rate of dissolving...
It's not.
Yeah, that's not what we're talking about. The extent of dissolving is what we're talking about. Yes? Okay. Gotcha. Thank you. All right. Let's have the conversation now. You guys have heard the phrases, I'm sure. Strong acid, weak acid, strong base, weak base. Okay. Neither of those terms have absolutely nothing to do with what an acid or base would do to you, for example. Okay? All it has to do is, now that you guys know what weak and strong refers to, is the extent of dissociation. For example, I always like to bring this up because some of you are familiar with this television show that actually ended 3 or 4 years ago, and nobody has ever... you guys may remember Breaking Bad, or the existence of it. Don't know if you ever saw it or not. I never saw it until after it was over. I waited till it was over before I ever watched any of it. But anyway, well, no. There were a lot of things that were true. There was one thing that I caught, anyway, that was not true, okay? Hydrochloric acid is a strong acid. Meaning what? It completely dissociates, okay? It completely dissociates. Whoa. Okay, boom, completely dissociates. Whatever we start off with here, it's completely converted over here, okay? Hydrofluoric acid turns out to be a weak acid. Notice how I can show that. What little technique am I using to show that it's a weak acid? The equilibrium arrows, okay? So as soon as this stuff starts dissociating, these two things, when they run into each other, we'll get to that here in a second, will reform this. So all three of those species are existing simultaneously. Okay, the scene that I'm referring to, well, actually there's numerous scenes that I'm referring to. What do you guys know about hydrochloric acid? How do you know it burns? It's currently in you. Most of you are utilizing it right now. Yeah, it's the main component of stomach acid. So yet, here it is, sitting in you, doing its thing. But if you poured some on your skin, well, it would certainly cause some damage, depending on the concentration and how much that you had on you, okay? Hydrofluoric acid is considered a weak... Okay, now, where do we keep the hydrochloric acid? Anyone know? What is this concentrated hydrochloric acid? 12 molar hydrochloric acid. Your stomach acid is around 0.1 molar. It's about 120 times more concentrated. Where is it stored?
In a glass.
In a glass bottle. Did anyone watch Breaking Bad? This is... Ignore anything that young lady just said, because it had absolutely nothing to do with what's currently going on. Okay, so anyway, can hydrochloric acid be stored in a plastic bottle? And to what extent, what's its concentration? 2 molar hydrochloric acid. Okay? So, concentrated acid could be stored in plastic or glass. Okay? Hydrofluoric acid, a weak acid. Does anyone know the scene I'm referring to?
Oh, wait. Oh, is it two?
Well, bodies, yes.
No, it was in the bathroom.
Bathtub. Okay, now what is a bathtub made out of? Porcelain, which is a form of glass. Okay, and what happened?
The body fell through.
Well, yeah, because the hydrofluoric acid reacted with the porcelain, and yeah. So, and it also did what to the bodies? Dissolve them, and it will. Now, will hydrochloric acid do the same? Yes, to a body, but not as quickly. Okay, and it can be stored in glass. Okay, so where I'm going with this is, are both of these acids harmful to us? Absolutely. So why do we call the one a strong one and one a weak? I think so many, pardon the pun here, laymen, get it? Laymen? Get it? Okay. Think the words strong and weak refer to the damage that they can do to us, when it has the only thing it has to do is with the extent to which they dissociate. Okay? I'm going to give you this list now. You're going to hear the list at least 2 more times this year. Okay? But the more times you hear it, I've found out over the years that it doesn't sink in as much as I would like it to, so the more times you hear it, the better off I hope we'll be. There are only 6 strong acids. Here they are.
Hydrochloric.
Hydrochloric.
Hydrobromic.
Hydrobromic. hydroiodic, sulfuric acid, nitric acid, perchloric acid. That is it. Now, again, I go back to, what does it mean to be a strong acid? Completely dissociates. That's the only thing it means. Completely dissociates. Every other acid is a weak acid, which means it partially dissociates. Are you guys good here? Well, you think you are. We'll find out when the actual questions start happening, okay? Now, I put a little asterisk beside the sulfuric acid. Sulfuric acid is only a strong acid for the first dissociation, the first hydrogen. There's two dissociations that end up happening. Anytime, and this is called a polyprotic acid, by the way, specifically a diprotic because there's two hydrogens. What does protic, do you think, refer to? A proton. What is a hydrogen ion? It's a proton, that's all it is. Because the hydrogen atom is a proton and an electron, right? To become positively charged, what do you have to do? Lose an electron. What's left? A proton. So a hydrogen atom, or sorry about that, a hydrogen ion is a proton. So this is why they call it a diprotic acid. There's two hydrogens there, okay? So when this dissociates, we get a hydrogen ion and a hydrogen sulfate ion, which then could dissociate further, but that dissociation is a weak acid, so that doesn't occur to much of an extent. This is a whole thing we're going to cover later. I'm just showing you what it means, why this is only a strong acid for the first dissociation. Okay. The strong bases, as we said earlier, are sodium hydroxide, potassium hydroxide. You know, we can get down to rubidium hydroxide. We said that strontium and barium are also strong. Okay. I could work in the magnesium and calcium here, but does anyone remember what I said about those? There's solubility issues there. They don't dissolve very well. To the very small extent that they do dissolve, it is a complete dissociation, but you just don't get very much dissolved. So, yes.
So the strong part means that
the extent of dissociation.
So the base is still completely, the strong base is completely.
There you go. There you go. Okay? Now, we're going to spend, and I'm doing this a little bit ahead of the game, okay? But it's okay, since we're on the, we might as well finish the whole discussion off. Now, what about a weak base? Magnesium and calcium hydroxide. The reason I put a little arrow here is because I said there were solubility issues here. Okay, now, what does a weak base do? How does it behave as a weak base? Well, currently, what are you guys noticing that bases have in them? Hydroxide ion. Acids have hydrogen ion that dissociates as a single species, okay, bases have hydroxide ions. Does anyone remember what this is? Ammonia. This is ammonia. This is a weak base. What do bases have? Say this again.
Why does it have hydrogen instead of hydroxide? Never mind. I mean, never mind.
Yeah, well, that's part of it. What do bases have that we know so far? Hydroxide ion. Where's the hydroxide ion? Oh, there we go. So now, a weak base behaves as a base not by providing hydroxide ion like those do, the strong ones do, but by producing hydroxide ion. Strong bases provide hydroxide ions. Weak bases produce hydroxide ions by reacting with water. You may have heard me say this when I had you before. Does anyone recall? Apparently Gracie does. Okay. What's that word?
Hydrolysis.
Good try. There you go. You put the emphasis on the wrong syllable. Hydrolysis. Now, does anybody recognize any parts of that word? Hydro means water. What does to lyse something mean? To what? Oh, no. Okay, do you remember a word called cytolysis? Who's in AP Bio? Oh, there you go. It's when a cytoplasm is the stuff that's in a cell. So cytolysis means the breaking of a cell. So what do you think hydrolysis means? The breaking of the water. What happened to the water? Well, if you think of water as HOH, what happened to the water? It got broken. The OH went off by itself, and where did this end up? With the ammonium, okay? So, a weak base produces hydroxide ion through hydrolysis. There you go. All right. Next. So, there's a little list of what, 4 substances down there? At the bottom of page 2. Maybe I'm wrong. There you go. Identify them as strong, weak, or non-electrolytes, and why. So, HClO4. Why? It's a strong acid. We just went over that. C6H, do I have 12 or 14 on there? 12. All right, that'll work. C6H12. We're just looking at whether it's an electrolyte or not. A strong, weak, or non-electrolyte.
I think none.
It is a non-electrolyte. It's not ionic. How about C? Yeah, it's mostly we would call it strong. And finally, the NH3. Right, for the reasons that we just talked about. Yes?
So if it has hydroxide in it, it's always
Yeah, with the exception of the ones that have solubility issues. Now, as it turns out, you notice I didn't put lithium on that list. It also has tendencies not to dissolve very well because of the force of attraction between the ions.
So
Moving on.
Should we consider it, if asked like a question on it, should we consider it?
You're going to find out. I don't want to go into this right now. Don't say it. I'm not even going to answer that question right now.
Okay.
Make a note. There's a reason why I'm not going to answer. I have things I have to get done today. That we'll come back to that. Okay, moving on to page 3. Let's look at page 4 first. Cross off page 4. Does it say the remaining concentration terms are useful? Blah, 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 blah. Yeah, get rid of that. There is one thing you can thank the AP for.
Prior knowledge?
Yes. They have eliminated that from the course. Now, I taught you molality last year. I also taught you percent by mass last year.
Molality.
Okay? So, anyway, moving on. Gracie, did you get that one?
What?
See, you missed it.
You got it. No, I got it.
Okay, all right, here we go. Anyway, as it says on page 3 at the top, the amount of solute present in a given quantity of solvent is a very useful tool, blah, 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 blah. Okay, molarity. We're going to focus only on molarity as far as solution concentration is concerned in this class. What is molarity? Well, as it shows you, molarity is the number of moles of solute per liter of solution. Turns out we may have to go back and revisit what it is to. There are two parts to a solution. They are solute and solvent. Solvent is what you are dissolving things into. Solute is what is being dissolved. I'm assuming this is also prior knowledge, but I've learned over the years that that's not always the case. So, in a sodium chloride solution, what's the solute? An aqueous sodium chloride solution. Sodium chloride is a solute, the solution is, or solvent is water. In this course, we are only going to consider aqueous solutions. I'm just saying. So that means the solvent is always going to be water. All right, moving on. Okay, so we can make ourselves a handy-dandy little equation out of this. Now, I put a V down there for volume. How you just need to know that your volumes have to be in liters. There is a mistake that you will make. If you're going to make a mistake, is forgetting to convert your volumes to liters. In order to use molarity, your volumes have to be in liters. Now, do we usually measure things in liters?
No.
No, we do not. Usually we measure things in
I'm sorry. I messed up. I'm sorry. Well, we measure grams of body. You can't even
When we're measuring the volume of a liquid, we're typically using instruments that measure in milliliters. So you're going to have to convert to liters by doing what? Gosh, dividing by 1,000. Thank you. All right. So anyway, how much time do I have?
10 minutes.
Actually, I have less than that. I want to have, I'm going to skip for a second because you guys can, here's the thing. And I've known this for a long time because I've been doing this for a long time. You guys can take an equation. Most of you can rearrange an equation correctly. And once you have that rearranged equation, you can plug numbers in and get an answer. That's why you're all sitting in this class. You have learned to do that skill. The one thing that you may not have learned is, what does that mean? And most of you are pretty familiar with this idea. You guys come up with answers because you're very good at plugging things into a calculator and pressing numbers on a calculator and having no idea what the answer means. Okay? So let's skip past all that for the immediate time being. Trust me, we're going to come back and revisit number 1. But I want to go down to the example at number 2 because that will help me and help you understand what's actually going on. Now, I've already kind of introduced the idea earlier in the period. So here's what we're going to do. Example number 4. Calculate the molarity of all of the ions in each of the following solutions. Well, I only gave you 2. We may come up with more here in a little bit. Okay? First of all, what can be said about each of those compounds? They are ionic. And how do we know they're ionic? Because there's a metal in there. I know I keep asking that question, but I'm telling you what, in March, there's still going to be some of you that don't recognize that. So I'm going to keep asking that question all year long. Who was it? Who was it? There was somebody. I believe it might have been Madison. But now that I look around, maybe it wasn't. What do you? How long do you have to know the information that we're learning right now?
It was me.
It was you.
And it is
Forever. Here's the one. This is the one thing, in my opinion, that makes AP Chemistry difficult. You have to know everything all the time. When we learn something, are we going to take a quiz on it? Probably. Are we going to have a test on it? Probably. And let's say we learn something in September. Guess how long you need to know that? Until May. Okay? Whatever we learn, whenever we learn it, you have to know it all year long. It keeps coming back. It keeps coming back. All right. So anyway, calcium, what is the name of that substance, by the way? Ooh, very good. Calcium hypochlorite. And being an ionic compound, if we're going to put that in water, what is it going to do? It's going to dissociate into a calcium ion and, be more specific, two hypochlorite ions. Would you guys agree? The initial concentration is 0.25 molar. Now, before I go anywhere else, and Gracie stay out of this, and Madison stay out of this, and who else? There was a couple of other people that were involved in this. Judy, stay out of this. Chelsea, stay out of this. What does this mean right here?
That's the amount of it.
What do you mean the amount of it?
The amount of, like,
Let me ask a better question. How many calcium hypochlorite particles are in this solution? No.
$6.022.
No.
What? 1 mole.
I understand that. I said in this solution, how many are in there?
Would it be... Never mind, I don't
No. You're headed in the right direction. You just haven't finished the thought yet.
So, because they're, like, in each, there's, like, there's 2 moles of this. Never mind. I don't want to say it.
Okay. If it were a 1 molar solution, how many of these would there be?
6 foot. Oh, so we divide that by 4. And then
Or multiply by 0.25. Either way, we have 1/4 of 6.022 times 10 to the 23rd particles. Are you guys following me? Remember, a mole is equivalent to Avogadro's number. You forgot that a little bit. I've already had conversations with students today, so I already know you forgot that. Okay? Yes, Carolyn. Because it's 0.25 molar. which means there's 0.25 moles for every 1 liter. Are you following now? Okay. So this refers to the number of particles in a volume. Now, if I had 1/4 the volume, then it would be 1/16 of Avogadro's number, 0.25 molar. Okay, but we'll let that go, okay? Now, when this dissociates, what's the stoichiometry between this and this? I found out earlier today that not everybody understands what that means when I say, what's the stoichiometry?
1-to-1.
It's 1-to-1. What's the mole ratio?
1-to-1.
Between this and that, it's a 1-to-1 stoichiometry. So therefore, what's the concentration of calcium ions? 0.25. What is the concentration of the hypochlorite ion?
0.125.
Gracie, we just got Joe. Did it sink in yet or not?
The knowledge?
Yeah. No, I meant to you.
Yeah.
You got it now. Chelsea, better? Good thing we had that conversation earlier today. Kayla? That's a palindrome. Huh. That's a palindrome.
She's like, my mom sent me up for this class. I'm like, mom's just like, take them home now. We don't need them in class.
So what happened here? Does it appear that we've created some matter? For some of you, Kayla, for you, it looks like we've, yeah, that's why I called you out, by the way.
What? I know what's going on. You both might as well do.
Okay, does it appear that we've created matter?
Yeah, but I know that we did make mistakes.
Tomorrow's away.
Kayla, do you understand this? No, you don't. You can do math. You don't understand it.
Yes, I do. I know why you did.
Okay. Then let me ask you this. What's that dissociate into?
3PL.
Okay. I know. Okay, now, according to this, it's 2 molar. What's the concentration of this? And what's the concentration of this? Excellent. Again, you can do math. Were the rest of you coming up with that? Okay. Some of you are. Some of you can do math, so you just do it. And the rest of you just don't get it yet. You will. I would like to make a drawing right now, but we have approximately 38.2 seconds left. So we're going to hold off on here. Tomorrow we'll come back and revisit. We'll do those examples just because you guys need to do that. And then we'll talk more about the significance of what's going on here.
Do we have calculate the whole or
Depends.
do we